All right, thank you. How was it? All right, good. How are you guys?
So since I started the assignment in Tuesday itself, because I received on Tuesday morning, I actually submitted the assignment at this point, but I had some doubts. So is there anything I can do and submit again, or should I just let it go instead? I've tried attempting it, but I'm pretty sure that I've not got it quite right.
Why don't you come to my office during office hours and see what we can do?
Next Tuesday.
Yeah. Well, no, I'm waiting next week.
Oh, okay, yeah.
Give me the following. The following Tuesday.
Okay. The next Tuesday.
Yeah.
How'd it go? Finished it, huh? Good, good. Very nice. All right, guys. So let's go ahead and get started. So you survived your first homework. That's good. I'm glad that you're able to turn it in. These problems will definitely help you out in the future when you go to do your research. You're going to have long analytic derivations that you have to do. So these are things that I remember doing when I was a student in this course. Okay, good. So let's get to the lecture. Is there any questions from the previous lecture? All right, good. Questions from homework? I guess we'll find out, right? Very nice. All right, good. So what we started talking about in the beginning of this module or this lecture was polarization. We started with current density, then we got to polarization. When we talked about polarization, we started with static polarization, right? We applied a static electric field to a dielectric material, and we were able to account for all of the induced dipole moments that were created due to that static electric field by introducing what's called the permittivity. The permittivity accounts for the contribution to the field due to the polarization. All right, but now we're going to introduce AC fields, AC excitation of dielectric materials, right? So time varying excitations. These could be sinusoidal. In this case, they are because we're dealing with time harmonic Maxwell's equations. And we're going to study the effects of what happens to a dielectric when you excite it with an oscillating electric field. All right. So here we have a kind of a cartoon that allows us to derive a differential equation and understand it from something we've learned before in our undergraduate physics class. So here we have an applied electric field. We're looking at the electrical equivalent here. We have a positive nucleus and a negative electron cloud surrounding that nucleus. The applied field is at the 0 point in its sinusoidal phase. And at that point, there is a perfect symmetry between the center of mass of the negative electron cloud and the positive nucleus. And therefore, no electric field will be generated. Here is a mechanical equivalent. We have a mass M affixed to a planar surface. That planar surface has friction coefficient D. So the mass is able to slide along this planar surface, and it has a coefficient of friction D. And there's a spring connected to the mass to its equilibrium point that has spring constant S. So when there's no field applied, the mechanical equivalent is everything is balanced. There's no motion, no displacement. All right. So when we apply the electric field, it has two cycles. It goes from 0 to maximum, and then back to 0, then to minimum. So when it reaches its maximum, the displacement is maximized, and we have the electrical equivalent in the following. We have the positive nucleus here. It has mass large M. It stays fixed. We have a negative electron, which is representative of the electron cloud that's stretched away from the nucleus. We have the induced dipole moment length, L, which is a vector, and little mass M attached to the electron cloud. All right, so it's displaced, it's stretched. The mechanical equivalent is we've taken the mass M and we've slid it across this plane by some distance, L, the same distance, and it now has a spring constant, right? So we've stretched the electron cloud due to the applied field, and if we were to let go of the electron or let go of the element by releasing the electric field, it would spring back to its equilibrium state. Same with the mechanical equivalent, right? All right, so then it goes back to 0, and then of course it goes the other direction, right? So we want to use the mechanical equivalent to derive a differential equation, which will allow us to model the displacement of the electron cloud with respect to the nucleus, the polarization of the atom, and therefore we can then derive what's called a dispersion relation. We can start studying the effects of applying an AC field to a dielectric material. So that's where we're at. We have a differential equation. We're going to use the mechanical equivalent to derive it. We all know the differential equation from Newton's laws is m d2L dt squared plus d dl dt plus SL, right? This is Hooke's law. This is the term that's due to the damping, right? But think about the door that you came into this classroom with. The door itself has mass, right? You have to apply a force to move the mass, move the door, open the door. But then it has a spring. If you push it, if you open it, then it closes itself back, right? So it has a spring that wants to close it, which is this spring. It has a mass, and it has a dampener. If you try to push it closed too fast, it'll push back on you, right? So the harder you push on it, the harder the door will push back on you, and it becomes harder and harder to displace it. That's a force proportional to the velocity, right? The faster I push it, the more the force pushes back. That's exactly this term here. It's proportional to the velocity, and it has some constant that characterizes how hard it pushes back. It's proportional to the velocity. dl dt is the velocity. So those three terms are there, right? Then we have the excitation function, or the forcing function on the right-hand side, the dipole charge, and the electric field as a function of time. Because a differential equation it's a temporal differential equation. We can write the electric field in time harmonics as E naught e to the j omega t. And now we have a differential equation we can work with. By dividing through by m and then defining some new constants, alpha and omega naught, we can start to analyze this differential equation, right? So there are three cases that we're going to analyze depending on the relative values of alpha and omega naught. Alpha is proportional to D, right? Which means it's representative of loss or resistance. Omega is not proportional to D, it's proportional to S, which is the spring constant, and therefore it defines its natural resonant frequency. That's what this is here, omega naught. We'll see why it's called omega naught soon, or why it's called the resonant frequency. If alpha is greater than omega naught, there's more loss than there is the natural tendency to be oscillatory. So we get what's called overdamped, right? It'll damp out, it'll die. If, on the other hand, alpha is less than omega naught, then the loss is not as good, not as great as the oscillating frequency, if you will. So the displacement. So what I'm doing here is I'm pulling it to some distance equal to 1 meter, and I'm letting it go and watching the dynamics. So this is not a continuous forcing function. It's a single displacement, and then I let it go. And we'll see it does oscillate, right? Because it's not damped enough to stop it from oscillating. Then there's a critically damped case when they're exactly equal, where it dampens fastest and goes directly down to zero displacement and stays there. All right? So these are some cases that we can use to understand this. Okay, so let me clear all this up. All right. Okay, so we went through this theorem, right? We need to understand what solution are we after, right? This now we're going to look into how what happens when we have a continuous excitation, right? Before that last plot is and understanding the differential equation when we displace it and let it go. Here we're going to continuously oscillate the mass. And we use this theorem of differential equations in order to understand how solutions are broken down. A general solution can be constructed by solving for the complementary solution and adding to it what's called a particular solution. The complementary solution represents a transient response, something that dies out with a certain amount of time, right? The particular solution represents the steady state response, and that's what we're interested in. So to get the complementary solution, we have to solve the homogeneous differential equation, because that's what the complementary solution is. It's the solution to the homogeneous differential equation. So the homogeneous differential equation means that the right-hand side is equal to 0. And we know we have constant coefficients, and we're going to differentiate some function and set it equal to 0. That's really good for us, because if we try a trial solution of e to the RT, we can differentiate that easily, and we're left with exponentials still. And because it's equal to 0, we can divide through by e to the RT, and we can remove all of the all the time dependence, right? Then we're left with just the coefficients. This works for constant coefficients. That leaves us with the algebraic equation that we can solve for the exponential, the power of the exponential function, right? The r. Okay, so we did this last time. So we found what R1 and 2 is. And what we found was that R1 and 2 is negative, right? And what that leads to is that all of these solutions will decay to 0 as time goes to 0, because e to the R12 into t, and R12 starts with the negative value, right? So the different cases where alpha equal to omega naught, this term goes to 0, you just get e to the minus alpha t, which is this. Goes down fast, right? The other case is alpha is greater than omega naught. So if alpha is greater than omega naught, then this term is there. You have a plus and a minus root, but alpha is greater than omega naught. So this will be less than that one, and still you'll decay, right? That's overdamped. Then you have this solution, alpha less than omega naught. You might have e to the minus t, e to the minus alpha t, but then you might also have a e to the j, right? E to the j omega t. So you get oscillation that's also damped. You get both the terms, e to the minus alpha t and e to the j omega t. Yes?
So is the Laplace domain, the transient response would be the same and the particular would be the j omega.
Yeah, you can think of it that way. The Laplace is in the Laplace transform is in the S plane, right? So you can have positive and negative. You can be on the right half plane or the left half plane. So you can have e to the minus a plus j omega t, or s plus j omega t, right? And then or alpha. And then you could have e to the plus. So it could blow up or it could decay. Typically it's stable if you're in the right half plane and so forth, right? Okay, good. All right, yeah, you can think of it that way. All right, so we got here. Now we got to solve for the particular solution. We solved for the complementary solution. We saw that it decays to 0 as time goes to infinity. Here we're going to solve for the particular solution using the method of undetermined coefficients. What we have to do when we solve a differential equation using the method of undetermined coefficients is we have to come up with a trial solution. Luckily, the right-hand side has an exponential in it. So a good trial solution is L naught e to the j omega t, right? Because we need to get rid of the time and end up with the algebraic differential equation after we plug in our trial solution. If we have a trial solution on the left side that has exponentials, and there's one on the right side already from the forcing function, then we can get rid of them all, right? Before, we had a 0 on the right side, so it didn't matter what we tried as the, it did matter. They had to be a common factor from all the terms so that we can divide through, right? And 0 divided by that is still 0. Here, the best trial function is something that has e to the j omega t, because when we differentiate it each time on the left-hand side, we can then cancel still, get rid of all of the time dependence. So that's what we do. L naught e to the j omega t. We can differentiate it once, differentiate it twice. This should be an L. And we plug that into the differential equation. And then we're able to cancel, divide through by e to the j omega t. And we're left with a algebraic equation. That algebraic equation, we can solve for the displacement. We can plug in our known constants that we defined at the beginning, and we end up with this function here, which is the displacement as a function of time, right? It's a linear differential equation. So we expect that the displacement is proportional to the driving function. So it is, right? It's e to the j omega t. So the displacement is also harmonic, right? At the same frequency. We have the E naught here appearing. And then we have this coefficient that we're going to study. That coefficient has all of the story embedded into it. So we'll look at different cases, but what it shows is if there is no loss, say D is equal to 0, frictionless platform, or the atom doesn't have any loss, right? If that's 0, omega is the frequency of operation. If we operate at the resonant frequency, then the displacement goes to infinity. So that means every little bit of power or every little bit of force that I apply to the system adds up in phase. So you add a little bit each time to the total sum, and they add up perfectly in phase. Resonance, right? Okay. The other case is when there is loss, even if you operate at the resonant frequency, then there's still some, the oscillations will end up being maximized at some point. Okay. So this is where we left off. Now we're going to define the AC permittivity. So assuming that the oscillating dipoles, which represent atoms of a material, are all similar and there's no coupling between dipoles, the macroscopic steady-state electric polarization, script P. Remember, script P. Script means that these vector fields depend on time as well, right? So we're still talking about in the time domain. P is equal to P of T. It's a function of time. Is equal to number of dipoles per unit volume times the charge times the length, right, by definition. And the length we just derived on the last slide using the differential equation, right? So here's the length. Then we can bring in, we can rewrite this as E, right? Okay, that's great. Because the next step is we can divide both sides by E. So what do we get? We get the complex permittivity. Is a complex number. Why is it complex? Because the displacement now has a complex component to it, right? There's some loss. Is equal to epsilon naught plus P divided by E. Right? Remember what the definition of P was. P was equal to epsilon naught chi times E, right? So P and E are linearly related. If you divide the two, you should get some units of permittivity. So this here is our AC permittivity. It can be separated into real and imaginary parts. The real part we describe or we denote as epsilon prime, and the imaginary part we denote as epsilon double prime. Complex permittivity. If you see a imaginary part in a permittivity, that's representative of loss. Where is this loss coming from? Say I have like dough, right? Baking some bread. If you need the dough, then it's going to heat up, right? Because of the friction between the molecules that make up the material. So if you keep kneading it, it's going to heat up. If I take a dielectric and I apply an oscillating electric field, it's going to oscillate back and forth, which is similar to kneading dough, right? We're kneading the material in a sense. We're going to heat it up because of friction between the atoms. The energy that you lose due to heat is representative of the loss. All right, so you can write this as epsilon r, the relative, if you divide through by epsilon naught, and you get 1 plus this, right? And you can separate that into real and imaginary parts. Good. Here's epsilon prime, the real part, and the imaginary part. I put them here for you. This is called the Lorentz model for dispersion. All right, very popular model. It has resonances built into it, losses built into it. Of course, this only captures one resonance, right? There might be multiple resonances at different frequencies. Then you have to have a summation and add up different omega naughts. But here we're going to concentrate on a single resonance. And this is called the Lorentzian model, right? We have loss and we have basically storage, epsilon r, the classical sense of epsilon r. All right? Yes. Was it him that discovered it? That's a great question. I should probably know that. It's named after him. I should probably look into the history of that. Next time I teach a class, I'll know that. But I'll look it up and I'll let you know next lecture.
Does Lorentz invariance have something to do with this?
Probably not. Lorentz invariants are dealing with coordinate transformations, right? Maybe. I don't know. I don't want to say for sure not. I haven't thought about that. Okay, good. So let's plot it. Let's look at it. Let's investigate it. So we have epsilon r prime, epsilon r double prime here. Let's make some observations. Epsilon r double prime attains its peak value at the resonant frequency omega naught. We expect that because the denominator becomes maximized when we're operating at the resonant frequency, right? So that's one observation. At resonance, the displacement is greatest. And since the frequency doesn't change, the velocity is greatest, right? Okay, so what I'm saying here is this. At resonance, the displacement is maximized, right? The other thing is, if the displacement is maximized and I don't change the period, say the period say the displacement is not maximized, but the period is the same, frequency is the same, then I only cover this much distance in the same amount of time. But if it's maximized, I cover much longer distance in the same amount of time, right? The atom is going, the electrons are going way further at resonance, back and forth in the same amount of time. So they're moving at a faster velocity. More distance, same time, faster velocity. We know that the loss in our differential equation was proportional to the velocity, right? Therefore, we should expect at resonance that the loss should also be maximized, which is kind of the bummer when we design materials using concepts of metamaterials and things, right? You get a lot of phase displacement. You get a lot of interesting effects near resonance, negative permittivities and things. But of course, you have to deal with the losses because of this. Since loss is proportional to velocity, the loss is greatest at this frequency. All right, great. So yeah, here is the displacement. It's maximized when omega equals to omega naught. And we have this term here, dl dt, which is the velocity is maximized, but that's the term that also models the loss. All right. So let's look at the plot over here. What do we have? We have the relative permittivity. We have radial frequency from 0 to 10. Radial frequency is omega. And here are the parameters. So there's our permittivity up there, epsilon prime and epsilon double prime. We're going to set NEQ squared over epsilon naught m to 1, just to plot this and understand it. D over m is 1, alpha over omega is 1/5, and omega is 2.5. All right, omega naught, the resonant frequency. Since omega naught is 2.5, where do we expect the loss peak to be? Based on this, right? First off, it's resonant at 2.5, right? Displacement is maximum at omega equal to 2.5. Omega naught is the resonant frequency of 2.5 radial frequency. Because the displacement is maximized at the resonant frequency, its velocity is maximized, the loss is maximized. So we expect epsilon r double prime, which is modeling the loss, to have a peak at omega naught, 2.5. This is epsilon r double prime here. So 2.5, we have the most loss at the resonant frequency, right? Look at the relative permittivity. It's most dispersive at the resonant frequency, right? It has the most change here. It goes like that, right? At the resonant frequency. Okay, great. Not near the resonance. When we're far away from the resonance, the epsilon r complex exhibits a positive slope, a normal dispersion, right? And near the resonance, epsilon r exhibits a negative slope, which is abnormal dispersion. You can exploit this negative dispersion in material engineering. Once you get good at understanding all this, then you can try to go back to these concepts and exploit them to find new phenomena hidden in Maxwell's equations through the interaction of electromagnetic waves with engineered materials, or science known as metamaterials and metasurfaces. So you have this anomalous dispersion, right? Metamaterials use this region to obtain a negative permittivity. However, the materials are very dispersive in this region, limiting the bandwidth, right? Okay, look here, relative permittivity, right? That means with respect to free space. what you guys understood in your last class in electromagnetic theory was that the permittivity can never be less than free space, right? It's supposed to be at minimum free space or better than that, right? Here, we can see that the relative permittivity is less than free space near resonance. Then you have to deal with the losses. So there are ways to exploit these properties of materials. Okay, the loss peak is inversely proportional to the resonance frequency. Okay, that means that the higher the resonance frequency, say I'm operating at a 5 here, right? Here's 5. The same plot, now omega naught is 5. We have alpha over omega naught 1/10, which means alpha is the same because omega naught doubled. D over M is 1, and this is still 1. So everything's the same, except look, the resonant frequency moved to omega naught equal to 5. So we get our peak at that value. We have less effect of the dispersion, and the loss is less, right? Because the peak of the loss is proportional to 1 over omega naught, right? This is all stuff that we're pulling out of those two equations at the top. Good. The real part approaches to free space when omega goes to infinity. Well, okay, so I wrote it there, but why do you think that happens? If I have an atom and I'm applying a slow oscillating frequency to it, then the atom can easily keep up, right? But if I apply like a super fast frequency, maybe beyond optical, like X-ray or whatever, right? It's oscillating so fast, by the time the atom starts to move this way, it has inertia. The input has already moved to the other side. And then it starts to react to that, and it's already moved to the other side. In the extreme case, it can't move at all. It's just, it has so much inertia compared to the oscillating, the input, that it doesn't react to it. What happens then? What does the material look like? Free space at those frequencies, transparent, see-through. There's no response, right? Of the material to the impinging wave. Okay, good. Any questions? All right. Let's introduce the loss tangent now. Let's investigate the loss. Yes.
Say that if we give the atom the velocity of infinity, that is imaginary, but if we give that velocity, then the material will become transparent. So is that the concept used for metamaterials?
I mean, so metamaterials, you try to go back to all these concepts and you try to exploit all of these little things to come up with new phenomena. You could, right? So there's metamaterials have so many different topics. Epsilon near 0, mu near 0, negative index of refraction. You can have anomalous dispersion, time varying. All of these properties. Normally, when you take class in electromagnetic theory, you think about isotropic, linear media. You think about homogeneous media, and you think about time invariant. All these things you go back in and you start to break these simple assumptions. So it's a fun subject. There's still things to be discovered in Maxwell's equations in electromagnetic theory, antenna theory, classical antenna theory. A lot of things are application driven now, so it's a little bit hard to make fundamental discoveries or things like that. So somewhat at the conferences, I'm saying this unbiased, all right? So there are antenna engineers that love, so don't, I'm an antenna engineer. I was an antenna engineer before I started studying metamaterials. But it's easier to publish if you're studying metamaterials, right? But even that, starting to get saturated because it's been 20 years now since they started looking at it. Okay, lost tangent. So, okay, now we go back to Ampère's law. The curl of H is equal to J impressed. So we can have an impressed current. We can have the conduction. Oh, man. Okay, that arrow is in the wrong spot. The impressed source is here. All right? The conduction current is here. The displacement current is there. Looks like I shifted the equation with respect to the... So I made all of these over the summer. It took forever. But anyway, some mistakes. So J omega epsilon C is displacement current. So we have J impressed sigma S into E. Remember, static. That's the static conductivity into E. J omega epsilon prime minus J epsilon double prime E. Why am I making the distinction that this is the static conductivity? Anybody? Remember, that's loss, right? Conductivity is loss, unless it's infinite. So we have static losses and we have dynamic losses, right? So where is the dynamic loss? Why didn't I say that this is sigma, what's that?
What's the DC loss?
DC, that's right. The dynamic loss is here. Epsilon double prime. We've accounted for that AC permittivity in this term here. The static conductivity is in that term, all right? They're both there, static and dynamic.
So then we have J omega in the first and epsilon prime minus J epsilon double prime. It's moving the loss to the imaginary axis in the S domain.
Yeah, we'll yes. Okay, so you might see that more here, right? So we have an equivalent, so okay. What's gonna happen? As you pointed out, the J is going to multiply onto these two terms. We have J and J, right? These two are going to become -1, that becomes plus. We have omega epsilon double prime. So see what happens. We had sigma, the static conductivity, plus the dynamic conductivity now as a real variable, right? A real quantity. Okay, we can lump those into what we call the equivalent conductivity, which contains both the static conductivity and the alternating field conductivity. All right? So impress source, now we have sigma into E, but this includes the dynamic and the static conductivity, both losses, and J omega epsilon prime E, this is just due to storage, right? Displacement, current. Good. So the total electric current density, we can call it the total current density, is impressed plus the equivalent conductivity into E plus the displacement term, displacement current. What can we do with this? Well, we can factor out the J omega epsilon prime. And what are we left with? We have J omega epsilon prime E, that's this part and the 1, right? Then we have sigma over omega epsilon, so we can cancel out these two omega epsilons, and we get J, and J is square -1 plus sigma E into E, right? So it makes sense. All right. So this quantity is very important. This, we call this term the loss tangent, all right? So we can write that as 1 minus J tan delta, where tan delta is the ratio between the effective conductivity and omega epsilon prime. What that's showing you is that the ratio between the loss and the storage, right? This represents the loss, and this represents you can see that here too, epsilon double prime divided by epsilon prime. Epsilon double prime represents the amount of loss, and epsilon prime represents the amount of storage. Or you can say the conduction current, the ratio of the conduction current to the displacement current. It's another way to look at this, right? That ratio will define boundaries between whether we have good conductors or good dielectrics or something in between, all right? We can also represent, why are we calling it tan delta? It's a tangent, right? It's a tangent of some trigonometric function, and there's an angle delta. This triangle is created. We have the displacement current here, J omega epsilon prime E. We have the conduction current here, sigma equivalent into E. We form a triangle with this. This angle here represents the ratio between the opposite over the adjacent, which is the tangent. So the angle delta is here, right? If we have no loss, what happens to this triangle? What happens? It collapses, right? This goes to 0. So no. This goes to 0, so it becomes a diagonal, right? Okay, good. So good dielectrics. If we have good dielectrics, so when you buy a dielectric substrate or material from Rogers, for example, they'll quote this effective loss tangent, tan delta and epsilon prime. If you have epsilon r prime and tan delta, you have everything you need for the material. Yes?
We have the conductor and the decay rate. Is that the loss tangent, how well it holds a charge at a specific point before it decays?
No, remember we derived that conductivity. If I impress a charge in a conductor, how fast does that charge decay at that point? Loss tangent is more related to, okay, so in that context, if you had, yeah, it probably would be related, right? I think that's more in the static conductivity though. The loss tangent has the static conductivity in it, so it's probably related to it, right? But it includes more than that. It also includes the dynamic components. Okay, so good dielectric, sigma over omega epsilon, is much less than 1. Why? Because the displacement current dominates in a good dielectric. It doesn't heat up much. There's not much loss, right? So in a good dielectric, we can approximate the current as J omega epsilon prime E. All right? In a good conductor, it's the opposite. Loss dominates. Displacement current is minimized. So we can approximate the current density as sigma E. All right? And here you see epsilon prime and tan delta for various materials. So a common one we use in the lab is Teflon 2.1 with a 3 times 10 to the minus 4. So this angle is super small, right? Hopefully it's small, right? Because you want to use it in applications where this triangle basically is almost all, sorry, it's this one. It's almost all displacement current. You want there to be no loss, right? Ideally. Unless you're studying metamaterials or something and you come up with some clever idea where loss is helping you do something, right?
Why does silicon not have no loss
Uh,
loss regard during the semiconductors don't have a loss tension?
it's a good question. I don't know. Just taken from the book. I would assume that silicon has a mobility associated with electrons. I'm almost positive it does. That mobility is finite. Therefore, the conductivity is finite. So it should be there. I don't know. It's a good question. Okay. So as I said before, there could be multiple resonances in your dispersion relation, right? There could be different frequencies where it goes through a different resonance. And here's an example. Here is P as a function of omega. This is in the frequency domain, epsilon naught chi e of omega, es of omega, right? Here is the axis, the omega axis. Then we have chi prime, chi double prime. You can do the same thing with chi. Remember, chi and epsilon are related by a constant. Epsilon is equal to 1 plus chi, right? So all of the things that we studied for permittivity, you can apply to the susceptibility as well. All right. There are multiple resonances happening here. Could happen at microwaves, at infrared, or even at ultraviolet. There could be a new resonance. So here we have different types of mechanisms that lead to polarization. One is the dipole polarization, the ionic polarization, or the electronic polarization. These are the things we talked about before, right? Okay, so they have different names, and those different names to different resonant frequencies. All right? Okay. All right. Let's talk about polarization current density. Now we have a collection of atoms. Let's say I have a material and I apply an AC field to that material. I have dipole moments that are oscillating all throughout the material, right? So you can replace the material with a mental picture or a model of a bunch of oscillating dipoles like that. A bunch of them, right? Okay. What is this? Now that it's oscillating, I have charges in motion, right? When charges are moving, that's a current. If they're accelerating, they radiate, right? So we can assign a current density to this time varying dipole moment. And that's what we're gonna do here. So the oscillating electron cloud constitutes a current density. Charges are flowing, right? So it is a current density. It's a bound current density, but it's a current density. So where can we find that on the right-hand side of Ampere's law? Because Ampere's law has all of our currents in it. Impress, conductive, and displacement. So we add our definition for our electric flux density. Remember, we defined that as epsilon naught E applied plus P, where E applied now is AC. And we plug that in for D, and we can separate that into two terms. J omega epsilon naught EA, right? That's the displacement current associated with the applied field in free space. And the P term is what accounts for the material, for the dipoles themselves, J omega P. So J omega P is a new current. It's a current density. This is used in metamaterials and metasurfaces. All right, so that's why I put this here. These are pictures from a paper I published. J omega P. So what can we do with that? We can, so okay, so what do I want to say? I'll get to this point after. So the current density is often incorporated by introducing the electric permittivity. So we have J impressed, J conductive, and then we have this epsilon complex in the E. We substitute the complex permittivity, and then we do the same thing where we distribute the J's, and we end up defining this effective conductivity here. And we have J omega epsilon prime E, right? So compare this to that, and what you'll see is that we don't normally see J omega P in Ampère's law, the way we've been writing it, because it's incorporated into this permittivity. That current density is part of this displacement current density. But you can explicitly separate it to a free space and a material component. Of course, it's here too, right? Epsilon prime is describing a material. But this is another way to write it. You can separate it explicitly by using the form at the top, right? So what can you do with that? So there are instances where time-varying polarization current is kept. Say a metamaterial or metasurface is a collection of polarizable meta-atoms arranged in a two-dimensional layer here at an interface, right? So assume that all of these are some inclusion that I put into a host medium that exists in a two-dimensional layer at an interface. Each of these polarizable inclusions can be modeled as, if it only has, the first order polarization, as an electric dipole and a magnetic dipole, right? Now I have an array of these polarizable inclusions. They might have magnetoelectric coupling, so I haven't said how these dipoles get created. The electric dipole could be created by an impinging electric field, but it also might be created by an impinging magnetic field. And if that's true, then these particles have what's called bionisotropy, and vice versa for the magnetic dipole. Anyhow, how do I model such an array, right? How do I model such a metasurface? The way I do that is by this boundary condition, which you can derive directly from Maxwell's equations. And what it says is, just like a boundary condition does, normally we say the difference, the discontinuity in H, right? The boundary conditions that we derived in lecture 1, we talked about the discontinuity in H created by surface currents, right? The discontinuity in H. What is the difference between H1 and H2 right at the interface? That discontinuity is proportional. Typically, it was proportional to surface current density J, right? But now we don't have any conduction currents. These particles are assumed to be polarizable, and they exist in a plane, meaning that they only produce the dipole moments, right? Now it's J omega P. And then we also have a contribution due to the gradient of the magnetization current. All right? And then we have Z cross delta E is proportional to the time varying magnetic current density. And then we can also get the gradient of the polarization current can lead to artificial magnetism. Okay. Okay, so let's talk about a very important concept here. You've probably seen this before. I don't want to get too deep into it, but it's called Kramer's Kronig. And what it is a relationship between the real and imaginary part of permittivity. So if you have one, then you get the other for free, right? They're related. So you can't design a material to have a particular permittivity, real part, and expect to be able to also design the imaginary part. They are hand in hand. You can only design one. The other one comes with it. It's related. So let chi of omega equal to chi 1 plus j chi 2 be a complex function of complex variable omega. So we have the real and imaginary part of susceptibility. You can think of that as permittivity because 1 plus chi is equal to epsilon, where omega 1 and omega 2 are real functions, right? Real valued. Suppose chi of omega is analytic in the closed upper half plane of omega and diminishes faster than 1 over absolute value of omega as omega goes to infinity. Do you remember what an analytic function means? Did you guys ever take complex analysis, complex functions? Analytic means that I can differentiate that function, and it satisfies what are called the Cauchy-Riemann equations. So, okay, analytic function means that it's a well-behaved function, put it that way. You can differentiate it. There's no singularities in that function. It's analytic in the upper half plane, right? And it has to diminish as you go out to infinity. That function has to decay to 0. All right. Kramer's Kronig relation says that chi 1 is equal to some function of chi 2. So if I know chi 2, then chi 1 is already known as well. If I design a metamaterial to have a chi2, a loss, a particular loss profile, then it comes with a permittivity profile, and I can't do anything about that. Or if I design a metamaterial to have a particular permittivity profile, the loss is defined, right? And what is this? This is called a convolution integral here. What it means is I'm sweeping some function, which is 1 over omega prime minus omega, across another function, chi2, and I'm adding up the results. I'm multiplying those two functions and adding them. I'm multiplying chi2 times 1 over omega prime minus omega. That's what this is, right? It's a product of two functions. And I'm adding up the result from minus infinity to infinity. And I'm creating a new function for what that product looks like at each frequency. That's exactly what's going on here. So here I'm showing both the real and imaginary part of a permittivity, right? This is the Lorenz model. So I have the loss at peaks, right? The red curve is the loss. It's chi2, which is the imaginary part. Chi1 goes through this Lorentzian dispersion, right? We saw that 2 slides ago, remember? Okay, so those two functions are related to each other by this convolution operation. So what am I showing here? This function is 1 over omega prime minus omega, like 1 over x, right? And I'm sweeping that across this function here. I'm sweeping it across omega 1, right? So, all right, let's see if we can understand this. At some point, when this function sweeps to the center of this peak, let's catch it at that point. Right when this blue dot, or right here at the peak, I get plus and minus contributions from the omega, multiplied by that peak, and I get 0 total, right? Try to stare at this. It's a convolution. And all it says is that I can get one curve from the other by doing the convolution with 1 over omega prime minus omega. All right? Okay. So the principal value, there's a PV there. It's a principal value integral. It denotes the value of the integral along the real axis ever except omega prime minus equal to omega. Because there, that function's singular, right? Okay. So by Cauchy's residue theorem, which I don't know if you guys remember this, but the integral of the closed loop integral of any analytic function in the part of the plane where this function is analytic is equal to 0, right? As long as there's no poles inside. Okay, so the principal value is from minus infinity to infinity. Why? Because this closed loop that I'm creating is the whole real axis plus the semicircle that goes to infinity, right? So imagine the whole upper half plane being covered with a semicircle. And remember what we said, the function has to go to 0 as 1 over omega goes, it has to decay faster than 1 over omega as omega goes to infinity. So as this circular part up here, C3, so this path integral, that closed path integral is C1, C2, and C3. C3 is off at infinity. So that part gives you 0 contribution. C1 now is the integral minus infinity to infinity, but excluding C2, right? Excluding C2. That integral, that gives me a value. And then I have this component due to C2, which you can calculate by doing a polar coordinate integral centered at that point. It's not important to understand. But what I'm saying is you can derive this expression from here, right? So just know from this slide that that the real and imaginary parts of permittivity are related, all right? All right, so what can we do with our Lorentzian model? This is the general form, Lorentzian model. Let's specialize it now to different cases, right? Let's say, remember our Lorentzian model was derived assuming a spring constant, a friction platform, and a mass m. What if we have no restoring force? What does that remind you of? No restoring force. What? No. If I have an atom and an electron cloud and I stretch it apart, the restoring force is what wants to pull it back, right? The spring. If there's no spring, a conductor has no restoring force. The electrons are free to move, right? Nothing's pulling them back to the nucleus because they're free electrons. So it's like a conductor. Or a free-flowing electrons can also be considered a plasma. So the complex relative permittivity up here becomes the following. Epsilon r complex is 1 minus NEQ squared over epsilon naught m. And then we have this term only, right? There's no resonant frequency anymore. There's no spring. So you can't hit a resonance, right? Because you can't apply a force in sync with a restoring force. Instead, we have just loss. We can model loss, and we have some operating frequency. All right, you can write this like in this form by defining the plasma frequency as this numerator and the component gamma as d over m. All right, and of course, this has a real and imaginary part as well. All right, good. This is called the Drude model, and it's used for conductors and metals. It's used a lot to model the dispersion of conductors. For example, it's useful for modeling metals. Some example Drude parameters are shown here. When you look up the Drude parameters to plug into this model, to model your metals in simulation, for example, I'll show you an example where I've done this. You'll get two numbers, the plasma frequency and the damping, right? These two numbers for gold, for silver, for gold, and for aluminum. All right? Okay, let's plot it and look at it. We're going to use the same parameters we used for looking at the Lorentzian model. But what happens now? We've noticed we lost the resonance, right? Now it just has epsilon prime is the blue curve, epsilon double prime is the red curve. So what happens at the plasma frequency? Let's say there's no loss first, right? Say there's no loss, so gamma is 0. What happens when omega is equal to omega p? When I'm operating, omega is my operating frequency. When omega is when I'm operating at the plasma frequency, you get 0, right? So 1 minus, this is omega p, this is 0, and omega p divided by that is 1 minus 1, you get 0 for permittivity. So if you're operating at the plasma frequency, the permittivity is 0. What cool phenomena can you discover or figure out when you have a material with 0 permittivity? What does that even mean, right? Go back to Maxwell's equations, infinite wavelength, right? There's so many things. You can start to dig into that. That's a field called epsilon near 0, or E and Z, right? Okay. So what you'll see is plasma frequency here is, okay. So the plasma frequency is here because there's loss. If there is no loss, then where's the plasma frequency here? 0 permittivity here, right? When there is loss, there is still a plasma frequency, but the permittivity is not 0. All right, what else can you notice? If I operate a metal at below the plasma frequency, then I can get negative permittivity, right? So one of the first metamaterials was an array of wires, vertical wires, right? From the floor to the ceiling, infinite long wires that are densely packed. So when an electric field comes in, oscillates, the electrons in the wires look like filaments of current that are going up and down, right? And all of these filaments of current that are going up and down model free-flowing electrons like a plasma. And I can engineer the radius and the spacing of those metal wires, aka filaments of current, such that I can design where the plasma frequency is at. And if I can design a material with a particular plasma frequency, then I can operate below that and I can get negative permittivity.
So in this case, what is plasma frequency? Is it like when you bombard gold to do sputtering? Or
No, I would not think of it that way. It's a frequency of the material becomes transparent if there's no loss, or when the loss is equal to the real part and the imaginary part's equal when there's that's how I would think of it. Okay, great. So let's make some observations. At the plasma frequency for lossless metal, epsilon r goes to 0. For lossy media, the plasma frequency is epsilon r prime when omega is equal to omega p is this, right? 1 over 1 plus omega p over gamma squared. In this case, the plasma frequency epsilon r equal to epsilon r double prime at the plasma frequency. However, this is not true in general. Okay. As omega approaches to infinity, the permittivity approaches that of free space. Right? If I take a metal and I illuminate it with X-rays, then it, okay, so that might be a bad example, but if you illuminate it with a high enough frequency, it becomes transparent. It looks like free space, right? Okay, it has to be very high frequency. At low frequencies, the metal has a very large negative permittivity, i.e. it's very opaque. Think of a reflection coefficient in terms of epsilon, right? So the reflection coefficient in terms of epsilon is epsilon R2 minus epsilon R1 over epsilon R2 plus epsilon R1, right? Or some function similar to that. So if one of those is very, very large compared to the other, you'll get a reflection coefficient which is near 1. Metals reflect very well at low frequencies, right? At very high frequencies, they start to look transparent. At low frequencies, they're very opaque. The permittivity is, normally it's like thousands, right? Okay, so where have I used this before? Here's a real life example. I've used this in an antenna coupled infrared photo detector. So here I have incident long wave infrared light at 9 micron wavelength. So it's a very high frequency in the terahertz, like 33 terahertz. And it's illuminating some array of what are called dielectric resonator antennas. They're small cylindrical dielectric pucks, if you will, that when they couple incident electromagnetic waves, they start to resonate and generate these cylindrical modes inside. We'll learn about all the modes that are generated in cylindrical cavities and waveguides the next semester. Okay, so these are designed such that the modes that are generated have a very high concentration, a hotspot at the center where we put a photodiode. So basically what it does, and the photodiode, the smaller the photodiode, the less dark current is generated, right? If I could just make this whole slab that's capturing this infrared light into a photodiode material. But if I do that, then I generate more dark current, which is the current output when there's no light input, right? That's noise. So you want to increase the sensitivity or the signal noise ratio of these by reducing the size of the photodiode material. The smaller it is, the less dark current it generates. But we still want to capture all the light and feed it into it. So we put this as a load to this cavity, and we still capture all the light, concentrate it, using that resonant cavity into the photodiode material, which is smaller. So we increase signal to noise ratio. All right, but how did I model these? There's gold on top, right, for contact. So you have to somehow draw out the electric current. The photodiode converts electromagnetic waves into electrons, right, photons into electrons. And you have to sweep these electrons out of the photodiodes by biasing it and having a conductive path for them to go. So there's metal on top, gold. The problem with HFSS, or if you try to design this in simulation, you want to put a gold, which is 100 nanometers thick, that has a skin depth of, where's the skin depth? I didn't put the skin depth, did I? Okay. The skin depth, oh, this is the slab thickness number of skin. Anyway, the skin depth is like nanometers, right? That means that in the metal there, we studied this in lecture 1, the electric field is decaying as e to the minus alpha z. Skin depth is 1 over alpha, right? The distance that you go into the metal such that the field is decayed to 1 over e. So in nanometers, I think it was 12 nanometers or so, in 12 nanometers into that material, the field has decayed to 1 over e. Then another 12 nanometers, 1 over e squared, right? So if I want to capture all of that dynamic in the metal and calculate the loss correctly, I'd have to resolve that electric field in there, which means I need tetrahedron in the metal, which will have side lengths of nanometers. 1 or 2 nanometers. I need a lot of tetrahedron in the metal, which is going to be very hard to run the simulation. It won't have enough memory to do that. So instead, what I did was I modeled this gold as a PEC, but has a sheet impedance around it that has the same loss as what you would experience in the metal. And the way we did that is, here's the skin depth. 9 is 1.595 nanometer, even smaller, right? To account for the conductive losses, when we need to resolve the fields, instead, this will require many tetrahedron. The lossy metal can be modeled as a sheet impedance with the same loss as the bulk gold material. So a sheet impedance exists right at the source, right? Here's the Drude model Drude, so I have a gold block in HFSS. I modeled it using the Drude, this Drude function, right? I found the gold parameters, the gamma and the plasma frequency for gold at 9 microns, plugged it into this model, plugged this function into HFSS, and assigned the permittivity to this piece of metal. Then I simulated it for different thicknesses. So the slab is thicker and thicker and thicker, right? As it becomes thicker and thicker, and then I calculated the power absorbed by calculating the transmission coefficient, the reflection coefficient, and adding up those and whatever was not there. If whatever reflects off, I have a certain amount going in. Whatever reflects off, I calculate that. Whatever transmits through, I calculate that. If I take the sum of the transmission and reflection and add it together and subtract it from the power at the port, then that must be the power that was lost, right? Absorbed into the gold. All right, so I sweep the thickness, I calculate the power absorbed, and I find that at 5 skin depths, it is settled down to negative 0.05 dB, for example. Then I took the sheet impedance, which is infinitely thin, calculated using these formulas. We're going to derive this all in this lecture later, and reflect it off of that, and it gives you the same loss, right? But it's a sheet. You don't have to resolve the fields in it. So you model all the loss at the surface. The way you do that is by using this, what's called the sheet impedance, right? We're going to look at this. We're going to derive this pretty soon. So that's one example, right? Where Drude models used and sheet impedances and so forth. Okay, one more model, the Debye model. When the acceleration is small compared to the other terms, right? So it's small displacements, right? Low frequency operation. When the acceleration is small, you can ignore it. All right, so that means the first term is 0. So let's try to solve this differential equation when the acceleration is small, right? If you do the same thing, you derive it, you get this model here. This is called the Debye model. So notice that there's no resonance now, right? There's no omega minus omega naught. There is loss, there's a plasma frequency, but there's no resonance. We use the same quantities here to plot it. And what we see is we have something that approaches here and approaches to, this is a useful model for like polar molecules, water, for example. I have a bunch of dipole moments and I apply an AC field to water like a microwave oven. When you put your food in the microwave, it's frozen and it comes out of the freezer, right? And if you put it in there, that frequency starts to resonate or to oscillate the water molecules that are dipole moments in the food, and they heat up due to the loss, due to the gamma. So in the absence of so permanent electric moments in the absence of applied field, the dipole moments can be caused to oscillate. These are sort of a oriental polarization, right? Not electronic. This is a model for that. Okay, let me think about van der Waals. Van der Waals, I don't know. There's probably a way, one of these models would probably fit it. All I remember about van der Waals is gecko's feet. So let me think about that. But okay. So the external applied field tends to orient to dipole moments. At some time t equal to 0, an external field was switched off, right? So we had some external field, we switched off the external field, and we're going to watch all of the atoms relax, right? The polarization vector will exponentially decay due to thermalization, right? Everything starts to become random again due to thermal energy. And it'll decay with this exponential factor. T is called the relaxation time, and it's dependent on the properties of the material. All right, this is an exponential decay. This is a model for that. This model I haven't seen used as much. So Drude's used a lot, Lorentzian's used a lot. But could be applications where this is used. Okay, let's look at what are called surface plasmon polaritons. So here we have an incident electromagnetic wave in free space. It's incident upon a material that has a negative permittivity on one side of the interface and a positive permittivity on the other. Why does this side have a negative permittivity? This is a metal, by the way. Why does it have negative permittivity? We just talked about that, right? Yes. Very nice. Good. It's a metal. You can have a negative permittivity if you operate below the plasma frequency. So whenever you have an interface, one side's a negative permittivity, one side's a positive, you can couple the incident electromagnetic wave into a surface wave, and that surface wave is called the surface plasmon polariton. So here's an animation of one such thing. So let's consider a TM polarized plane wave. I understand we haven't studied in-depth TM polarization and what that means, and we're going to look at plane waves next lecture, but hopefully you remember from your last course. Incident upon a planar interface. So the total electric field here, tangential electric field, is eta times cosine theta times n cross h. Don't worry about the details here. We're going to learn to calculate all of these. Okay, so cosine theta can be normal divided by k. We'll learn about that next lecture too, but maybe you remember it. So k normal is in this diagram kz, and k is all of k, right? It's omega squared mu epsilon or 2 pi over lambda n cross h. So okay, so here's k normal right here. So here, and when we solve the wave equation, we'll understand this too. Don't worry if you don't understand these things. We're going to study them. We're going to learn all of this. So then we have this relationship here, right? So since the wave impedance, which we're also going to learn about next lecture, is the ratio of tangential field components, and the tangential field must be continuous. At least we know that tangential field must be continuous. The wave impedance must be continuous as well. Wave impedance is the ratio of tangential E to tangential H. And we know that tangential fields have to be continuous. So the wave impedance is continuous. So the wave impedance on one side of the medium is equal to the wave impedance on the other side of the medium. All right? For evanescent waves, normal to the interface. So, yeah, okay. So for evanescent waves, normal to the interface, K tangential has to be greater. All right, what do I want to do here? I'm debating on whether I should skip this until we study all these properties of waves. Do you guys remember any of this? Wave impedance, evanescent waves, dispersion kx plus ky plus kz equal to k, kx squared plus ky squared plus kz squared equal to k squared. Do you guys remember that from last course? All right, I'm gonna skip this then. We'll come back to this. Try to remind me because it's a super cool topic. And we derived the dispersion relation here, and what we see is stop bands where waves can't propagate, and we derive and analyze the dispersion relation for surface plasmon polaritons. Super cool concept, super cool topic. But we got to try to remember to come back to this later in the course. All right. We talked about permittivity, right? We talked about permittivity being proportional, a proportionality constant between D and E. But we assume isotropic materials where E was proportional to D directly, right? So dx was equal to epsilon ex, dy was equal to epsilon ey, dz was epsilon ez. But there are materials, we're going to learn about these materials in depth and how waves propagate through them, that have what's called anisotropy. And there we have a relationship between epsilon or D and E through a permittivity tensor epsilon, which is a matrix now that can mix components. So D and E may no longer be parallel. All right, so materials may be classified as linear or nonlinear, right? Materials whose constitutive parameters are not functions of the applied field are linear. They could be homogeneous or inhomogeneous. Materials whose constitutive parameters are not a function of position are said to be homogeneous, right? Dispersive or non-dispersive. Materials whose constitutive parameters are not a function of frequency are non-dispersive, and anisotropic or isotropic. Materials whose constitutive parameters are not a function of the direction of the applied field are called isotropic. All right? So what if it's anisotropic? So we have this relationship then. dx is related to ex, ey, and ez now, if that matrix is full, permittivity matrix, right? So ez could give you a dx. So things can get mixed up. And you can exploit all of these properties in you designing new materials. Assuming homogeneous, non-absorbing, and magnetically isotropic media, the energy density of the stored electric field, we saw this formula in lecture 1, in an anisotropic medium is now epsilon dotted with D. So this is the time script E and D, epsilon I, or EI, epsilon IJ into EJ, right? So you can store energy in different axes, depending on different applied fields. Take the derivative of energy with respect to time, you get power. We have this expression. So remember, the net power flow into a lossless unit volume has divergence of S equal to 0, right? If it's a lossless medium and flow, whatever power flows in flows out. It's not a source or a sink. So the divergence of E cross H, which I have some volume, I'm looking at the power flowing out, the energy density inside must be equal to the decay of energy density inside, right? Divergence of E cross H conjugate is epsilon into partial t, H into partial B partial t. This we had in the first lecture. Now we can replace what we have for D as epsilon E, and we have this expression, right? And we're assuming that it's magnetically isotropic. So since the Poynting vector corresponds to energy flux in the medium, right? The first term on the right-hand side must be equal to du dt. This term, right? Has to be du dt. This whole thing. All right. So we have, this term has to be du dt. So we have du dt here on the left, which is the flux, right? The flux of energy that's traveling out of a volume is the rate of power flow, which is the change in energy density, right? That is equal to epsilon ij dej over dt, which is this term here. Okay, so you can go through this. The whole point of what this is to show you that the dielectric tensor must be symmetric and contains only 6 independent components. This is called Hermitian media. All right, if the medium includes loss, complex epsilon, and conservation of the electromagnetic field energy requires epsilon ij equal to epsilon ji conjugate. Still Hermitian, but there's a relationship between the components of this permittivity tensor. We're going to come back to this exact slide next lecture when we get into wave propagation in anisotropic media. So all I want you to take from this slide as a takeaway is this here, that anisotropic permittivity can have, anisotropic media can have a permittivity tensor, and it relates D to E in that way. All right? Good. Okay. So you guys have probably heard of diagonalizing a matrix. I'm going to skip this as well, and we're going to come back to this exact slide when we talk about anisotropic media, wave propagation in the media. We'll come back to this, all right? Those same slides are in the next lecture. Okay, so that's all permittivity, all right? Can be anisotropic, could have a tensor relation, could have AC variation, there could be loss, leads to complex permittivity. There could be static conduct or static. If you hit it with a DC field, then you have a static permittivity. And I want to, okay, let's just get into this real quick. What time is it? 39. So now we're going to study magnetization. We're going to derive permeability. We're going to do almost everything all over again, but for mu. All right, but we'll do it faster now. So what are the origins of magnetization and permeability? Now we have to come up with a model. Remember before we had a model of the nucleus, the electron cloud, an electric field applied to that atom, and the electron cloud stretching away from the nucleus, right? Separating the plus and minus center of masses, creating an electric field in between them. Energy stored in the form of an electric field. Here we have a different model now. Our model for the magnetization of a material includes a nucleus and electrons orbiting the nucleus, classical model. All right, so here we have a nucleus, positive charge. The negative electrons are orbiting around that nucleus in a circle, right? Okay, well, the electron is in motion in a circular path, means charges are moving along some path. That's a current, right? We can constitute that as a current. So really, the electron orbiting around a nucleus can be modeled as a circular current. All right? That circular current, if you multiply the current, the I of that circular current, right? So this has some amps per meter, or amps rather. This has some amps. If you multiply that current strength by the area that that current encloses or that it sweeps around, then you can define what's called a magnetic dipole moment. Remember the electric dipole moment was related to Q times D, which is the displacement, right? The charge, the value of the charge plus Q minus Q. So Q multiplied by D, which was the displacement. I think we called it L. And the L vector went from minus to plus, which is backwards, right? Dipole moment dP was equal to Q, the value of the charge, multiplied by dl, right? All right, here, our dipole moment is going to be I times A. It's right there. N hat, it's a vector now, right? The other one was a vector too. It's a vector, and it's equal to I don't know if you can see this. This says D M I is equal to N hat I D S I. So it has a vector normal to the area enclosed by the loop. It's proportional to the area enclosed by the loop, and it's proportional to the current carried by the loop. Yeah? Magnetic dipole. Now, you get the same magnetic dipole as long as the areas are equivalent. Doesn't matter what shape the path is. All right? Could be a rectangular path. This just shows same dipole moment as long as the areas are enclosed are the same and the path, the strength of the current is the same. Yeah? Okay. So the magnetic dipole moment of a single electron is this equation here, and it's in amps meters squared, the units. Remember what the units of the dipole moment were? The electric dipole moment was dp I was q into dl, right? So this is coulombs meters. Here we have amp meter squared. Why is that? Why do we have squared instead of just meters? It's an area, very good. It's not a length. Good job. Okay. Yep, let's end here. We'll come back to this, all right? All right, so someone try to remind me later in the course to come back to the surface plasma and polariton dispersion. I think you'll get more out of it if we push it till we can understand it more. More around like lecture 4 or 5. Good. All right, guys. Don't forget, a few announcements. I'm going to be gone next week. I'm at a conference. So you will have a recorded lecture to watch next Thursday. Next Tuesday, class is canceled outright. Next Thursday, there's a recorded lecture that will be uploaded. If instead of watching the recording, you want to come to the live recording of it, because I'm going to record it and then upload it later, I'm going to record it in this room tomorrow at the same time. So if you'd rather watch it live, come to the course tomorrow, this room tomorrow at 9:30, and you can watch it live, then you don't have to watch the video next week. If you don't want to come tomorrow, then I'm going to be in here recording it. I'll upload it in the middle of next week. You have to watch it next week. All right? And then I'll be gone all next week. And the following live class, if you don't come to tomorrow's recording, is the Tuesday after next. All right? Okay, good. All right, see you guys. Hey.
So,
Next time you need to turn this in before class starts.
yes, I
You walked in late? Okay, that's okay. Yeah, I saw you the whole time anyway. All right, but no problem. Thank you.
So I have a small request, maybe the next week or after that, can you explain a little bit what happened physically when the longitude of the wave is infinite?
Oh, yeah. The wavelength, right?
Yeah.
In epsilon near 0. So,
When the plasma frequency is equal, I mean, when the frequency is equal to the plasma frequency, that rest,
see ya.
the
Yeah,
longitude of the wave becomes infinite.
yeah. That's great. Yeah, I can definitely do that. So if you go back to all the fundamental expressions in Maxwell's equations, we're going to derive all of those. Like the
Because I'm working
wavelength.
with Plasma physics, so some concepts of the metal that you talk about plasma, I can see.
Yeah, for sure. Yeah, we can talk about that. Let me know. I didn't know you're working with plasmas. That's cool. Yeah, I'm sure you guys have seen the Drude model then, or you've heard of it, right?
I heard about it like 1 week ago. So I was studying something about plasma,
Okay,
then I get into this more.
very nice. Well, yeah, let me know
Yeah, we will talk about it.
for sure. All right, interesting. Woo!